A neural network doesn't naturally speak in probabilities. When it finishes thinking, it hands you a vector of raw scores called logits, and those numbers can be anything at all. Positive, negative, huge, tiny. So how do we turn that mess into something we can read as a confidence, like a 70% chance this image is a cat? The answer is one small, elegant function that shows up at the end of nearly every classifier and inside every attention layer of a transformer. It's the Softmax function, and today we're breaking down exactly what it does and why it's everywhere. Let's frame the whole point with a single before and after picture. Raw logits are just unbounded scores. A number like 4.2 or -1 or 100. They tell you the relative ordering of the options, but they aren't probabilities. They don't sit between 0 and 1, and they certainly don't add up to anything meaningful. You can't hand them to a user as a confidence. Softmax transforms those scores into a proper probability distribution. Every output lands between 0 and 1, and together they sum to 1. Larger logits earn exponentially more probability, but crucially, every option keeps a little. It's a soft, gentle version of just picking the maximum, which is where the name comes from. Here's the actual computation, and it really is only a couple of moves. Start with the raw logits straight from the model. Say the network scored 3 classes. Those 3 numbers are your input, and right now, they carry no probabilistic meaning at all. They're just the model's uncalibrated opinion about each option. Exponentiate each score. Raising e to the power of every logit does 2 useful things at once. It forces every value to be positive, and it amplifies the gaps, so a slightly larger score pulls noticeably ahead of the rest of the pack. Divide each exponentiated value by the sum of all of them. This normalization step is what guarantees everything lands between 0 and 1 and adds up to exactly 1 across the board. In practice, you subtract the largest logit first, a small trick that keeps the exponentials from overflowing. And out comes a clean probability distribution. Each class now has a share of the total confidence. They all sum to 1, and you can read them directly. That vector is what feeds the loss, the prediction, or the attention weights downstream. So let's pin down the 3 ideas that make Softmax worth understanding deeply. Exponentiate, then normalize, and you get a distribution. That 2-step recipe is the entire function. It converts arbitrary scores into positive numbers that sum to 1, ready to be read as probabilities. A temperature knob lets you tune the sharpness. Lower it, and the distribution grows peaky and confident, concentrating on the top choice. Raise it, and everything flattens toward uniform, spreading the probability out. Same logits, very different behavior. And it's genuinely everywhere. The final layer of classification networks. Next word prediction over an entire vocabulary, and the attention weights inside every transformer. It also pairs beautifully with cross-entropy loss, because together their gradient simplifies into something remarkably clean. Let's lock in the 4 essentials before we finish. Softmax turns a vector of raw logits into a probability distribution, where every value is positive and they all sum to 1. It works by exponentiating each score and then normalizing by the sum, giving larger logits exponentially more probability while keeping some for every option. A temperature parameter sharpens it toward confident or flattens it toward uniform, and a stability trick subtracts the max logit to avoid overflow. It's the beating heart of classifiers, next word prediction, and transformer attention, and it pairs cleanly with cross-entropy loss. If you like seeing the math behind AI made this clear, Standarity.com is packed with explainers just like this one. Come explore.